Welcome, Michelle. I'd like to now turn it over to you to begin today's presentation. Michelle?
Thank you very much, Chris. Hello, everyone. My name is Michelle Viani, and I'm a Product Applications Engineer in the High-Speed Converters Group at Analog Devices. Today, I will be discussing with you a very popular topic these days in the communications industry regarding cellular networks and the increasing demands on the performance and capabilities of these systems, and how a variety of analog devices, gigasample per second DACs, enable communication companies to meet these growing needs. Our products provide ultra-wide bandwidth capabilities that are increasingly required as these sophisticated systems evolve. Here's a quick overview of the agenda for today's presentation. I'll start by giving a brief review of the wide variety of end markets that these gigasample per second converters can service for some general background. I'll then focus the discussion on the communication industry backhaul solutions, talking about some of the wireless backhaul choices that exist today, as well as a brief overview of the market and its current trends. I'll go into some more detail regarding the system specifications for these backhaul solutions, including architecture overviews. To wrap up, I'll discuss how Analog Devices converters provide solutions to these backhaul system requirements and provide some details on a few of our converter products and technology. I'll finish up with any questions or comments you may have at the end of this presentation. As most of you are probably already aware, the increasing popularity of mobile phones, especially smartphones, has exponentially grown over the past few years and is projected to continue to grow at increasing rates as we move towards 2020. More mobile devices equipped with data capabilities place increasing data demands on the cellular networks that provide the data and create complex problems that service providers need to solve in order to meet the performance expected by their mobile customers. As shown here from the Cisco Visual Networking Index report last year, they predict mobile data usage will have a compound annual growth rate of 57% from 2014 to 2019. The main driver in this mobile data increase is the use of smart mobile devices that access these mobile networks. In 2014, almost 500 million mobile devices and connections were added from the previous year, totaling 7.4 billion devices and connections globally. And of that 500 million growth, 88% were specifically smartphone additions. In a report from Ericsson, mobile subscribers are expected to grow from 5 billion in 2010 to 9.2 billion in 2020, with 80% of those subscriptions being broadband capable. The network speed capabilities of these broadband subscriptions will vary regionally depending on the deployment of more advanced systems over the next few years in different parts of the world. At the moment, GSM edge-only subscriptions are the largest percentage of the mobile subscriptions today. However, Ericsson predicts that HSPA GSM subscriptions will begin to take over in the next few years, with LTE beginning to increase soon after as more LTE systems are deployed into 2020. They predict 85% of mobile subscriptions in North America will be LTE by 2019. With all this increase in data and capacity demands, this places heavy burdens on the backhaul solutions required to transfer this data throughout the network. Currently, 3 main mediums are used for backhaul: copper, fiber, and microwave. Microwave is expected to continue to account for at least 50% of mobile network backhaul transmission, with copper slowly being replaced by fiber where cost and deployment complexity is justified. Regional differences will play into the decision of laying fiber versus setting up microwave links. Sometimes, areas may already have decent existing fiber infrastructure to utilize, whereas other areas of the world may have limited support, and it may not warrant the cost and time for creating such an infrastructure. These differences vary drastically across the globe. For example, 90% of the backhaul systems in India and the Middle East are marked microwave, whereas less than 10% of the backhaul systems in China are microwave due to higher fiber network availability. Overall, microwave systems can provide the high-capacity needs for these backhaul systems into the future while being flexible, reliable, and at a low total cost of ownership and quick deployment pace, making them ideal for this fast-growing and demanding cellular network market. Next, I'll begin to talk about the various microwave backhaul solutions that currently exist. First, a quick overview of a few of the end application markets that gigasample per second converters can support. This table shows the differences in the applications and their channel bandwidth and allocation bandwidth ranges. The cellular communications market, along with the traditional or legacy point-to-point microwave applications, have relatively small channel bandwidth, with slightly wider allocation bandwidth possible across operators. The E-band point-to-point microwave systems are architectured, however, for much wider channel bandwidth, up to 2 gigahertz channel spacing currently, with a very wide allocation bandwidth at the E-band microwave frequencies. Cable television is similar to cellular communications, with relatively small channel bandwidth. However, their allocation bandwidths are larger, especially with the movement towards DOCSIS 3.1 standard and beyond. Military and radar technology bandwidth requirements can vary widely depending on the application. Things like electronic warfare applications or military communications may require very narrow bandwidth for some designs, whereas others will require extremely wideband capabilities. Similarly, the instrumentation market also varies depending on the end product design. Often, the instrumentation needs to follow along with the cellular bandwidth requirements, as they often are driven by test equipment demands for things like 5G test beds and other cellular protocol testing. Overall, the variety of markets that these gigasamples per second DACs can serve require the products to be flexible in how they can be configured to support both narrowband and wideband applications. For this discussion, however, I will primarily focus on the microwave market segment, both for the traditional legacy band and E-band point-to-point application space. As I mentioned previously, there's increasing demand for higher capacity, and the growth rate is exponential, meaning rapid deployment of network systems is critical to staying competitive in the market and meeting the industry needs. Therefore, often fiber or copper is not feasible given the timescale of these deployment schedules. These diagrams depict the variety of different network designs of these microwave systems that can be used in order to transfer data back to the main aggregation base station site. For the long-haul sections over 10-kilometer distances, typically traditional or legacy band microwave systems are used for the data transmission. For the shorter hauls, traditional band can also be used, as well as the higher frequency architectures like E-band may be employed. The E-band systems provide much wider bandwidth and a higher data rate throughput than the traditional band systems. Overall, the combination of traditional and E-band microwave systems support up to 50% of cell sites currently, with millions of these systems deployed across the world to date. This diagram shows a breakdown of the transmission frequencies used in the different point-to-point systems. The traditional microwave bands span from 6 gigahertz up to 42 gigahertz, with the 6 to 8 gigahertz range typically being used for the long-haul transmission and 11 to 23 gigahertz range used for the short transport and aggregation portions of the network. Due to the increasing demand for data and bandwidth, more bands are gaining popularity in the 26 to 38 or 42 gigahertz range as well to provide additional capacity support in the traditional bands. In these traditional band systems, the individual channel bandwidths vary from 3.5 megahertz up to 112 megahertz. These bands, though relatively narrow, require high-performance components in their systems as they use high modulation data transmission schemes that need high signal-to-noise ratio performance. The other frequency ranges at the higher outputs are V-band at 60 gigahertz and E-band at 70 and 80 gigahertz. The higher microwave frequencies mean the antenna sizes are smaller, and their output power is typically lower than the legacy band systems. Due to environmental factors such as oxygen absorption, weather susceptibility, and fast channel fading properties at these high frequencies, They tend to only be used for the shorter range or small cell applications, covering smaller distances than traditional band. The channel bandwidths, however, are much wider, up to 1 to 2 gigahertz bandwidth requirements in E-band, for example. The achievable capacity differences between legacy band and E-band is fairly significant, with E-band being able to potentially deliver up to 10 gigabit per second throughput rates. Additionally, this range typically has light licensing or no licensing requirements for the operators, which helps for total cost of ownership for these systems. This comparative table shows each of the different frequency band allocations for the different wireless backhaul solutions. It shows the comparative channel sizes I mentioned on the previous slide, as well as the capacity and coverage distances typical for each system type. Another key aspect is the modulation scheme used for each of the network types. The traditional band systems use significantly higher modulation orders to increase their throughput despite their narrow channel sizes. This requires higher performance metrics of the components in these systems, especially the signal-to-noise ratio of the data converters being used. In the V-band, E-band system, however, the modulation order is much smaller, which allows for relaxation of the required signal-to-noise ratio of the converters. These high-frequency systems are able to obtain a higher throughput rate compared to the traditional band due to the much wider bandwidths available at these frequencies without needing to increase the modulation density to achieve higher capacity. These microwave systems are point-to-point architectures and typically use frequency division duplexing, or FDD, where they separate the transmit and receive frequencies to be in two separate bands to allow for full duplexing system capabilities. They require a line of sight for optimal performance, whereas the non-microwave RF frequency bands can support non-line of sight. This next section contains a brief review of some of the key specifications for point-to-point microwave systems. Point-to-point microwave systems today use quadrature amplitude modulation, or QAM, sometimes pronounced QAM or QAM. The basics important to point-to-point capacity are shown in this slide. The figure shows a constellation plot for 16 QAM. You can see that 4 bits are used to describe one symbol in this 16-symbol array. In this case, the L factor is 4. Each symbol has a unique amplitude and phase associated with it, and these are